Okay, so how are the assignments coming? Okay. Are they, give me a little feedback, 1 to 5 on how they're coming. How are we doing? Oh, okay. Okay, so what can we do to fix that? I go through, well, okay, I mean, we can, that's fine. What parts are causing troubles? There you go. Okay. Yeah, spring is crazy. So I have a suggestion. Would it be good to maybe go through some practice problems? Would that be good? Okay. All right, let's do that. Let's call an audible here. So why don't you throw out some suggestions of problems you'd like to see? Like, break out your Chromebooks and look at the assignments and tell me which kind you want me to talk about. So which assignment are we going to? It'd be like, I know it'd be one of the 5.3s, I'm guessing, right? Okay. 5.3.2. Okay, that's kind of what I figured. Got something for you. There you go. You betcha. Okay, 5.3.2. And let's have a quick look at a couple of these. Give me an example. What's 5? Okay. Okay. All right. Okay, something like that. That be it? Okay. Okay. Let's talk about how we do this. So it's real important that we understand, like the vocabulary is really important here. Yeah, it's got to make sense what they're saying. So let's take each statement and let's carefully interpret that and turn it into some algebra stuff that we can do. So we got this polynomial function. Part A, it says list each real zero and its multiplicity. So what am I doing? What does this mean? Each real zero. Okay, so the zeros of a function are where the function has a value of 0. Okay, and when we say the function has a value, are we talking x or y? Y. Yeah, the function f of x is equivalent to y, right? So when we say the value of a function, we're talking about a y value. So we're trying to know where is the function which is equal to y, where does that have a value of 0? So where is it 0? Okay, so we're going to turn this into that equation, right? Graphically speaking, where do functions cross, or where do functions have y values of 0? On the xy plane, where would that occur? Say it again. Where is y equal to 0? The x-axis, right? So we want to know where is the function at, or where does it intersect or cross the x-axis. So I'm just reminding you that real zeros are always equivalent to x-intercepts, right? So this is the equation that we're going to solve right here. Okay, well, it's done, essentially, isn't it? The math gods already did all the hard work for you here. It's already factored. So we want to find the zeros. How do I go about finding the zeros here? What do I do to get there? What do I do to find the zeros? I'm just applying, what's that property called? Well, what's the property I would apply here to find the zeros? It starts with a Z. The zero product property. There you go. And I want to make sure we get all this stuff. So what does the zero product property say? Well, if I've got a product of factors, the product of factors can only equal 0 when the individual factors are equal to 0. So I need to find the zeros of the factors, right? So let me say this real carefully and slowly. The zeros of the factors are going to correspond to the zeros of the function when it's written in factored form like this, right? Only where the individual factors are equal to 0 could the product, and therefore the function equals 0, right? Give me 1 to 5 on that. Is that making sense? Okay, we get that? Again, only where these individual factors have values of 0 could the entire function multiply to 0, right? Okay? So we just got to find each one of those. Okay, so let's take this one. What's the 0 of that factor? 5, yeah. When we say the 0 of the factor, what does that mean? What's the 0 of a factor? And I know I'm throwing around lots of words, but I want you to make sure you understand the vocabulary. What's the 0 of a factor to find that? Yeah, where the factor is 0, meaning the number where it's equal to 0, right? The x value, okay? So what is, you already told me, didn't you? It's x equals 5, okay? And then how about this one? -4, okay. So those are our two zeros of the function, because those are the places where the function ended up being equal to 0. Okay, what about the multiplicity? What's the multiplicity here? What do you think? Rachel, can you tell us what's the multiplicity? You remember? You might have been gone that. I can't remember who was here that day. Not many. But who was here? So help me out. Somebody be brave. Raise your hand. Yes.
Like 5 would be 1. It's like how many times it's used.
There you go. Okay, good. So it's how many times does that function appear in the product? Well, x to the 5th, or x minus 5 is really just to the first power. It only ever shows up once. And so the multiplicity for this guy equals 1. X plus 4 cubed, isn't that the same thing as x plus 4 times x plus 4 times x plus 4, right? So that factor is showing up 3 times, and you don't have to think about it that way. Just look at the exponent, right? If it's x plus 4 to the cubed, whatever the power of the factor is, that corresponds to the multiplicity of that factor or that 0, okay? So for this one then, the multiplicity equals 4. Okay, make sense? Okay, give me thumbs on this. I want to make sure before I move on. Are we good? Okay, question?
I thought it would be 3.
Oh, sorry, 3. Yeah, why did I put 4? Man, what was I doing there? I don't know. Do not know what was going on. my head there, but oh, that's 4. I know what it was. Okay, now I figured it out. Figured out what it was because I saw the 4. There you go. Okay. I'm easily distracted. All right, so next part. What are we looking at? Determine whether the graph crosses the x-axis or touches the x-axis and turns around at each 0. So we've got the 0, x equals 5. What's it doing there? Is it cutting or bouncing? It's cutting. How come? Yeah, because it's an odd multiplicity, right? Odd multiplicities cut the x-axis. Even multiplicities bounce. Okay, and so this one's going to cut. And we could even be more specific. It's going to cut like a what? Like a knife? It's going to cut like whatever the power of that, whatever the multiplicity is, it's going to look when it crosses the x-axis like the parent function for that power of x, right? Well, x to the 1 or x minus 5 to the 1, that's linear, right? So it's going to cut it like a line. Okay, what about at x equals negative 4? What's it going to do there? Bounce or cut? It's going to cut, isn't it? Because 3 is odd. Okay? I think on your example, it probably was a bounce. That's probably why you said bounce. It's going to cut. If we want to be a little more specific, though, it's going to cut like what this time? It's going to cut like an x cubed function, so it's going to cut like a cubic, right? So that when it cuts through the x-axis then, if this is the x-axis, it's going to look like this. It's going to come down and graze and turn like a cubic function. Okay? Making sense? Okay? Okay, what else? Let's go through a couple more, how about? Yes?
Could we go over 16?
Yes, we can. Same assignment? Yep. Yeah, okay, this is kind of a bonus one. This is a little tricky. Okay, I'm going to do this a little differently. Okay. Okay, this is going to be really hard to see. If I go, let me see something here. I think I'll have to do this. Work problem as a student, okay? Okay, let's make a little change on this. Boy, is that what it looks like when you do this? Wow, that's really hard to see, isn't it? Yeah. Huh. Okay, are you able to type coordinates in? That's pretty tough. Okay, so what would we get here if we're trying to graph this thing? Where are the x-intercepts going to be? Where are the zeros going to be? 1, negative 3 and 0, right? So I would do one of these guys. I'm going to make a cubic shaped function, and I'm going to have x-intercepts at negative 3. Oh.
It was at negative 1, 3.
Oh, yeah, okay. So now I want to know, can I change that? If I go up here. Oh, man, this is kind of tricky, huh? think I got to cancel. Do that again. Okay, there. So see, look, I can see. One thing that makes this a little bit easier is that when I put my cursor down here, I can kind of watch the coordinates in that box up there to make sure I get it right. Everybody see that as I move this around? It's going to change the coordinates of where the pointer is, so I want to get it right on -3, 0. I want to get it right on 0, 0. And I want to get it right on 1, 0. Okay, but now what? I'm going to need another point. Okay, so on this one, what's my other point going to be? Well, I've just got to pick a value of x and plug it into the function and get a y value that I can use. So like what would be a convenient y value to pick? Something like, how about something that's going to be a small number? Like what if we picked -1 or something, right? Like I don't want to pick too big a number because I'm going to start, like if I pick a number like 5, I'm starting to get a pretty big number when I multiply all those things together, right? Everybody see that? Can you guys see this? I mean, that's pretty small, but can everybody see what I'm doing here? So my function is, and if you want to write this down on your scratch paper, here's the function in case you can't see it. Our function is f of x equals 2x times x minus 1, quantity x minus 1, times the quantity x plus 3, okay? We want to be able to find one other point because in order to get the exactly right function, I've got my 3x intercepts on there, but let's think strategically about this. How many points determines a line? 2. How many points do I need to determine a parabola, so a quadratic? 3. How many points do I need for a cubic, which is what that's going to be if I multiply it out? I need 4, don't I? And so I've got to pick one other correct point. Okay, so we can do that. Say it again.
Could you do f of 1?
We could do f of 1, but if I do f of 1, I'm going to get back 0 because I already know that's an x-intercept, right? I want to pick a different point, and I want to pick one that's going to give me small numbers. So I would probably choose -1 because 1 is small, and that's like the smallest convenient number that's not a 0. You don't have to. I could pick 3, or I could pick -2, or I could pick 4. But if I pick 4, I'm just starting to get kind of big numbers in there, right, that I'm multiplying together, and they may not stay on the graph. All right, I want to do this so I can draw on stuff. There we go. Okay, so let's do a little, let's evaluate this function. So again, our function is, I'll make this a little bigger so you can see it. Our function is f of x equals 2x times x minus 1 times x plus 3. So if we do f of -1, what's my first factor going to be? What's 2x if I'm evaluating this at x equals -1? 2 times -1. So that part, if I put parentheses around that to section it off, that's going to give me -2, right? What's -1 minus 1? -2. Okay, and what's -1 plus 3? 2. So if I multiply all those together, -2 times -2 is 4 times 2 is 8. So isn't that telling me that for an input of -1, my output is 8? Everybody see that? So I can come back then and make my fourth point at -1, 8, and I got this. So how do I do this then? I got to go back here. There we go. So -1, 8 right there. And again, how am I getting it? Because I'm looking at the ordered pair at the upper right of the graphing tool. Okay? And we got it. Okay, make sense? Okay? Okay, what else? Any other questions we want to go through? Yes, Melody.
Number 7.
Yeah. Okay. Okay. Yeah, that's a good one. I tell you what, I've got one set up like that already. Let me look. I set up some review problems, and we'll just use one of those now. One like that, right? Isn't that what we're doing? Yeah, like that? Okay. Okay, good. So let's do one like this. So in order to graph this polynomial, and we're just going to, they give you multiple choice, right? You get to choose which graph it is. Okay. So let's graph this one. What are the clues I need to graph this thing? Really, all I need to know is I need to know where the x-intercepts are, right? What is happening at each x-intercept? Is it cutting? Is it bouncing? What's it look like when it crosses the x-axis? And what the end behavior is. And that's enough for me to sketch the graph, okay? So let's figure out the end behavior. How about we'll do that first? So if we take this function, g of x, and if I multiply the whole thing out, all I care about is what's the leading term. I don't care about the rest because the leading term determines the end behavior, doesn't it? By the leading coefficient test, right? We know all we care about is the leading coefficient and the degree to get the end behavior. Okay, so what am I going to get if I multiply this whole thing out? What's the leading term of that factor going to be? Everybody see what I mean? Like if I take this factor right here, if I were to expand that whole thing out, what's the leading term of that factor going to be? X squared, right? I'm just going to get x squared plus other stuff, right? But all I care about is the leading term. What's the leading term of the blue factor going to be? X cubed, right? Everybody see where we're getting this stuff? Any questions on that? Okay. So I get x cubed plus some stuff. And then the red factor, the leading term is the only term in that factor, right? So that one's just negative x. Well, if I distribute the leading term to the leading term and then take that result and distribute it to the next leading term, if I just propagate that all the way through, if I were to multiply this thing out, it'd be very complicated. It's going to be a big, ugly polynomial. It's going to take me a while to get. But the leading term is easy to find. Right? What am I going to get if I multiply x times x squared? Or negative x times x squared? Well, negative x cubed. Take that answer and multiply it by x cubed, and what do I get? Negative x cubed times x cubed is what? Negative x squared, or x to the 6th, right? Plus a bunch of other junk. So use your arms. Tell me, what's the end behavior going to look like of this thing then? If it's negative x to the 6th is the leading term. What's it doing? Okay, no. Falling on both. Yeah, and how come? Let's review why. Okay, because what happens if we have an even polynomial, right? Its positive end behavior, like positive leading coefficient for an even polynomial is like this. How do you remember that? Think of the easiest one. Think of x squared. What's x squared do? Does that, right? You could also, if you want just a quick little mnemonic device to just remember this stuff so you can, as you're doing it, think about it this way. What's the number of endpoints that are pointing up or down? 2. 2 is even, right? Now, if it's odd behavior, if I have a positive leading coefficient and an odd degree function, that's doing this, right? It's rising to the right and falling to the left. What's the number of endpoints that is pointing up or down? Only 1, which is odd. Only 1 is pointing up, 1 is pointing down. That's odd. So if this is positive even, that's positive odd, what's negative even? Right? Just going to flip it, reflects it over the x-axis. If this is positive odd, that's negative odd, right? Okay, make sense? Okay. So we know this is giving us That kind of end behavior. We don't know what's going on in the middle, and we don't care as far as the end behavior is concerned. We just want to know what's going on way out to the left and way out to the right. Okay? So where are our x-intercepts? Where's the red x-intercept on this one? Allie, where's the red x-intercept? If that's my red factor, what's the 0 that goes with that? X equals, if I'm setting the whole, think what we're doing. If I'm finding the zeros of the function, I set it all equal to 0. What's the value of x that's going to make the first red factor 0? 0, yeah. Okay, so we got x equals 0. 0 is one x-intercept. How about the green factor? Annika, what's our green 0 going to be for the green factor? 2. Good. How about the blue factor? Ashton, what's the blue 0 going to be? -3. Okay. And we already know the end behavior, so we're starting to be able to put the pieces of the puzzle together, right? We know this is down on the left and down on the right. Now we just got to fill in the pieces in between. Okay, so what's this thing going to do at the first one? If we start at the right and kind of work backwards, doesn't matter. If we start out here and we're going to work our way backwards, what does the 0 do at 2 based on the multiplicity? What's going to happen at that x-intercept at 2 based on the multiplicity of the green factor? Right? So what we're asking about here is how does it interact with the x-axis? It bounces, doesn't it? How come? Even. It's going to bounce because the multiplicity is 2, so it's going to act like an x squared graph, right? Which is a parabola that bounces off the x-axis. So this thing is going to do this. Man, I got to calibrate my board. That's off a little bit. Come on. Oh, this isn't good. Something bad's going to happen here. This thing's about to crash, I think. It's starting to act funny. So it's going to do that. It's going to bounce at the green one. How about the red one? That's the next one we encounter. Show me with your fingers. What's the multiplicity of the red 0? Okay, 1. So what's it do? What's the multiplicity of 1 do? Going to cut like x to the 1. It's going to cut like a line, right? So then we know when we switch over to red behavior, this thing has got to turn around and cut through the x-axis. And then how about at the blue one? What's it going to do at the blue one? What's the multiplicity? Show me with your fingers. For the blue function? There we go, right? 3. So what's an x cubed graph look like? What's that do? Kind of show me, just draw it in the air a little bit. What's x cubed do? There you go. Yeah, it's the one that's going to come down, graze, and turn, right? So it's going to cut it. If we want to be, do you really have to know that? I mean, not really. You could probably get by just having it cut through the x-axis. But when you get to calculus, you're going to want to be a little bit better than that. You're going to want to know kind of what it looks like, right? So we want to think about what's the nature of that. It's cutting like a cubic. Question? No, okay. So then when I flip to blue mode, flip to blue mode, this thing's got to turn around, and now it's going to do something like that. That's a pretty bad picture, but you get the idea. I mean, see what I'm going for there? Okay? That help? Okay. Anything else you want to see? Any other examples? Okay. I'm guessing maybe you want to. How many people are done with the assignment? Anybody done? Okay. Okay. Then I'm going to show you one more thing then, just so people that are done can move on. This will just take a second, though. It's not a big deal. This is not really going to show up on this test, but it's a good time for us to bring it up. Okay. I think we did that one. Right here. Fundamental theorem of algebra. Here's a really convenient way to state the fundamental theorem of algebra. This isn't actually how it's written, but it's a great way to think about it. And in an Algebra 2 class, this is how we want to know the fundamental theorem. Just says this. Fundamental theorem of algebra says if a polynomial of degree n has exactly n complex roots every single time, including multiplicities. So what we mean then is if the multiplicity of a 0 is 4, then that counts for 4 roots, right? 4 solutions or 4 zeros is what we're talking about. When we say roots, that's interchangeable with zeros. Okay, but remember, only the real zeros correspond to x-intercepts, right? Like if I were going to, and I'll just remind you, I can't remember if we did this or not. We did it a long time ago, but I can't remember how recently, so I'm going to do it again real quick. There's a parabola. What's the degree of a quadratic every time? 2, right? The degree is 2. And so I'm guaranteed to have 2 complex zeros. In this case, they're both real, and so I get 2 x-intercepts. Everybody see that? Both of them are real. Okay, what if we do one like, what if we do one like this? What if I have a parabola that just grazes the x-axis? Again, it's a parabola, so n equals 2. How many zeros does this thing have to have? If the degree is 2, how many complex zeros does it guaranteed? How does it have? It's got 2. Absolutely for sure it's got 2. But multiplicities count multiple times. So this only has one x-intercept, but that x-intercept guaranteed is going to have a multiplicity of 2. Okay? Last example. It's a parabola, right? It's quadratic, so guaranteed the degree is 2. It's got 2 complex zeros. Are they real? Thumbs up or thumbs down? Remember, real zeros always correspond to x-intercepts. So thumbs up if they're real, thumbs down if they're non-real. Yeah, they're non-real. They have to be. How do you know? No x-intercepts. Yeah, if there's no x-intercepts, then in this case either can't be any real zeros. They're both complex. They would both, if we were to set this equation equal to 0 and solve, what's going to be in our answer? What are we guaranteed? We're going to have i's in our answers, aren't we? And both of our answers are going to contain i's. Okay? All right, so let's look at this example right here. So what's the degree of that polynomial? Show me with fingers. Everybody, what's the degree of that? You got to do a little calculation. Okay, if I were to multiply it all out, what would be the power of the leading term? That's all we're asking. Yeah, it's going to be 5, isn't it? I'm going to get an x times an x squared times another x squared. It's going to give me an x to the 5th, right? So the degree is 5. How many complex zeros does it have for sure? 5, yeah. For sure. What's the max number of x-intercepts it could have? No, could be 5 x-intercepts, right? Whatever the degree is, that's the maximum number of real zeros we could have. How do we know that? Because if it's guaranteed to have 5 complex zeros, couldn't they all be real? Potentially, right? Turns out they can't, but we'll talk about that later. There's a tricky reason why they can't, but for now we don't know that. It's for that. Don't worry. I shouldn't have even said that. Don't worry about that part. Forget I said that. As far as we know, they could all be real at this point, right? And so the answer is 5. Okay, we'll alter that a little bit in the future, but the answer is 5 for now. Okay. They could all be real, right? Okay. Or theoretically, they could be you know, there's some of them could be complex also, and we could have less than 5, okay? Well, let's see what happens here. If I want to find the zeros, this thing is already set into factored form, which is really convenient. So all I'd have to do is set the function equal to 0 and find the zeros of the factors, right? Okay, well, let's find the red. The red one's easy. Red one's absolutely trivial. If I want to find the red 0, I just set x equal to 0, and there it is. There's my red 0. Okay, how about let's do the blue 0. If I want to find the blue 0, I'm going to take the blue equation and set it equal to 0. Okay, and I got to solve that. What are my magic numbers? Well, -2 and -2. Everybody agree? Give me thumbs on that. Does that make sense? Okay, so isn't that the same thing as saying x minus 2 squared equals 0? Right? Okay. What's my 0 then? Show me with fingers. What's the blue 0? In other words, what's the value of x that's going to make that factor 0? Yeah, it's 2. Good. Okay. What's the multiplicity? Got to be 2, doesn't it? Because it's a factor that's being squared. Okay, so let's count up our zeros. There's 1. Here's 2 and 3. Okay, all we got to do is find the green 0. Okay, let's do that. So the green 0. We need a little more room. Let's come down here and do the green 0. Okay, can you find magic numbers that multiply to 2 and add to 1? No numbers that multiply to 2 and add to 1, are there? Multiply to positive 2 and add to 1. Okay? So it doesn't factor. Does that mean we couldn't have real solutions? No, they could just be square roots or fractions or something, right? Okay, so let's probably try the quadratic formula. Okay, but if we're going to try the quadratic formula, where do we want to start? Because if I find out that, if I can determine that I'm going to only have non-real zeros, do I even need to solve that equation if I'm looking for x-intercepts? Right? If my zeros are going to be non-real, are they going to correspond to x-intercepts? No, only real zeros correspond to x-intercepts, right? So the place I'd want to start in the quadratic formula is the discriminant, right? The part that's in the square root. Because if I find out the discriminant is negative, I can stop. I don't have to do any work, right? So what is the discriminant? B squared minus 4ac. That's going to give me 1 squared minus 4 times 1 times 2. Is that going to be positive or negative? It's going to be negative, isn't it? Right? The discriminant is going to equal a negative number, so no x-intercepts. Right? No x-intercepts because we have non-real zeros. Okay? Does that make sense? Okay, do you see? Now, how did we get non-real zeros here? We got non-real zeros when the discriminant ended up being negative, right? That's the only way it could happen, right? If we're going to solve for quadratic factors, because I can always use the quadratic formula to solve a quadratic equation, every time. Sometimes I can find easier ways, but it always works, right? The only way I could get non-real solutions would be if I had a negative number inside the square root, okay? But that means if I'm using the quadratic formula, there's a plus and a minus in the quadratic formula. So I'm always getting back 2 imaginary solutions at the same time. They always come in packets of 2 or in pairs, right? So we have this other corollary to the fundamental theorem that says this. a polynomial of degree n has exactly n complex roots, including multiplicities. But if a plus bi is an imaginary 0, then its complex conjugate is guaranteed to also be a complex 0. Okay, because how come? Because that's the plus and that's the minus in the quadratic formula. Imaginary solutions or non-real solutions always come in complex conjugate pairs every time. You could never have a singleton. They always come in pairs, complex conjugate pairs. So then we could go back here to this statement. Annika, I'm going to clarify all this confusion we had earlier on this. I could see the exasperation. You were wondering why I was telling you one thing and it seemed like it should have been one thing. It wasn't. I was throwing curveballs at you. Okay, the number of x-intercepts that it could possibly have then. If it's a 5th degree polynomial, it could, okay, I was wrong about that. It could have, I don't know what I was thinking. It could have 5 real zeros. But could it have 4? Think about this. If the total number of complex zeros is 5, they could all be real. That's possible. They could all be real. Okay, they could all be 5. So that's not even a for now. That one's, I don't know why I said that. That was my mistake. So we got extra, double, triple confusion on that. No, 5 is the answer. But could we have 4? How come? Because if we had 4 reals, that would leave how many imaginaries? 1. And can you ever have singletons? They always come in pairs, right? So it's impossible to get 4 real solutions. You could get 5, or you could get 3. 3 would work, because I could have 3 reals and 2 imaginaries. I could never have 2 reals, though, because that would give me 3 imaginaries, and I can't have an odd number of imaginaries, right? So I really could only ever have 5 or 3 or 1 real zeros in this one. Okay? Is that making sense? Okay? All right. Good talk.